A motor oil at a temperature of 80 Celsius degrees passes through a tube of 8 millimeters of diameter and 86 centimeters in length. Yes, I'm too lazy. What is the difference of pressure that is going to be needed to maintain a flow rate of 2.5 milliliters per minute? Okay, and they're giving me the N, which in this case is the coefficient of viscosity of this motor oil. What do we have to do? First of all, if viscosity is part of the given, that means that you have to work. I know what I did. Okay, yeah. Anyway, I'm sorry. So, what do we need to know for this exercise, or what tells me what equation to use? First of all, if I give you the N, okay, if I give you this N, and of course it's measured in Pascal seconds, you need to know that it's viscosity. And if it is viscosity, it's Poiseuille. So what do you need to know? Okay, first, you need to organize your data, okay? In Poiseuille, we don't care about the temperature. We care about the temperature in chemistry right now that we're working with temperature. In physics, we are not working with temperature. So this temperature of 80 degrees is just extra information, context information that is not useful to solve the problem, okay? It's just telling you that it's 80 degrees the temperature, okay? Now, that tube has 8 millimeters of diameter. So that is a data that I really care about. But more importantly, what is the equation that we need to use for Poiseuille? Take a look. Okay, according to Poiseuille, the flow rate is equal to pi r to the 4. I'm gonna write it better. Okay, this is the equation that we're gonna use. Difference in pressure divided by divided by 8 times that viscosity times the length. Okay, that's exactly what I need. I don't need temperature for this exercise. Okay, so I'm going to list my given according to what I need. I don't need diameter, I need the radius, but I know that I can get the radius from the diameter. So my diameter is 8 millimeters, and of course I know that I have to convert this to meters. Okay, so I know that there are 1000 millimeters in 1 meter. Okay, so this is equal to 0.008 meters. I'm gonna go for my calculator better, okay? I don't want to mess it up. Okay, I'm back. Okay, what else? In length, it says that I have 86 centimeters in length. So length is equal to 86 centimeters, and I need to convert to meters. So this is gonna be, in 1 meter, I have 100 centimeters. So this is gonna be 0.86 meters in length. Okay, the projection of the whiteboard is slow. Sorry. It is very slow today. That's something that is out of my control. Okay. What is the problem asking me to find? If you participate, it will be better. Yes, exactly. I need to find the difference in pressure. That means that delta P is going to be my unknown. Okay? It's okay if you write in scientific notation. I don't like it, but it's okay. I mean, I don't like it because it takes more time to do it in scientific notation, but yes, it's correct. Then it says to maintain a flow rate of 2.5 milliliters per minute. Okay, so they're giving me a flow rate that is 2.5 milliliters. Okay, I'm gonna make a change here. Instead of minutes, seconds. Okay, now it makes more sense. Remember that you write it as a fraction in a way that you can cancel the units. Okay. I need to convert this into what? Remember, SI units for flow rate are gonna be cubic meters per second. So I need to convert from milliliters to cubic meters. I'm not going to touch the seconds. So this conversion is gonna be, I have 1000 milliliters in 1 liter, and I have 1000 liters in 1 cubic meter. Okay, now you're gonna have cubic meters per second. So 2.5 divided by 1 million. Now this one is good that you write in scientific notation. In that way you're going to skip to write all those zeros. So how much is this in scientific notation? 2.5 times 10 to the negative 6 cubic meters per second. Okay, now we have everything we need. I'm sorry about all these zeros. And I have the n already in Pascal seconds. So what do I need? I just need to apply the formula. Okay, this is the formula, and all I need, no, wait, I have diameter. Exactly, I mean, I have the diameter, I don't have the radius, so I need to find the radius. From the radius, remember diameter divided by 2? So this radius is going to be 0.008 meters divided by 2, which is 0.004 meters as a radius. Okay? Now, what I need to do, I need to apply the formula. So, this is my equation, and I will isolate for delta P. Okay? So the first thing that I do is all this term that is dividing, I will send it to the other side to multiply. Okay? So I'm going to have 8NL multiplying Q equals pi radius to the fourth power, change in pressure. Equals to pi radius to the fourth, change in pressure. Okay, I'm looking for change in pressure. So this term that is here is multiplying the change in pressure. So I'm going to send it to the other side to divide. Okay, so my equation now is going to be transformed to 8NL Q divided by pi radius to the fourth equals to my change in pressure. Okay, what I need to do now, just I just need to work with my givens. So replacement of your given 8 times n, that viscosity is given in the problem as 7.8 times 10 to the negative third power Pascal seconds. The length, that is 0.86 meters. The flow rate, that is 2.5 times 10 to the negative 6 power Pascal seconds. Sorry, cubic meters per second. No, esta cosa. Wait. All this divided by 5 radius to the 4, the radius, that is 0.004 meters raised to the 4th power. I know. This is very slow, guys. And this is equal to the change in pressure. Okay. Now, in your calculator, this is the beautiful part of it, okay? In your calculator, it's going to be 8 times 7.8 exp minus 3 times 0.86 times 2.5 exp minus 6 divided by pi, and then divided by 0.004 raised to the power of 4 equal. How much you got?
166.81.
Okay. So, my change in pressure is equal to 166.81. Now, the cancellation of units are going to be meters times cubic meters is going to give you meters to the 4th. They're going to be cancelled with these meters to the 4th. And these seconds from here going to be cancelled with these seconds from the flow rate. So in general, the final unit is going to be pascals. What is the complexity of this kind of exercises? Well, in my opinion, none. But maybe what you can find difficult is the use of the calculator. So I'm going to leave you the process here. If you didn't get this answer, let me know right now in the chat or in WhatsApp so I can send you the video how to do it. Okay, those who told me that, I'm gonna send you the video after the class is over so you can apply the procedure in your calculator. Okay? Those who said me, okay, those students text me after the class is over so I can send you the procedure, a video of the procedure in the calculator. Okay? But send it to me a message in WhatsApp. Okay, so we continue. This is the exercise, the exercise that I gave you the other day about Bernoulli's equation. It says water flows at a rate of 25 liters per minute through a horizontal 7 centimeter diameter pipe under a pressure of 6 pascals. At one point, a certain point, calcium deposits reduce the cross-sectional area to the pipe of the pipe to 30 centimeters square. What is the pressure at this point? Consider the water to be an ideal fluid. Now, we started this exercise in class, and of course we needed to start with the conversions. Okay, the 25 liters per minute conversion, you convert these liters to cubic meters like this, and from minutes to seconds like this, and you will get this flow rate. Okay, 417 rounded. Now, what else? Diameter, that is 7 centimeters, you convert to meters. Okay, and that's what you get. The rate from the diameter, you get the radius, and from the radius, I'm not very sure if we did if we calculate the areas. I think we did, but I'm not very sure. And then, well, information. Okay, information about the pipe. The pipe where the diameter is 7 centimeters, you have this pressure. Okay, and in the other side where the area is being reduced, you have a different pressure that is exactly what we're going to find. Okay, and remember, because it says that it's water, that means that we're going to be using the density of the water. So one thing that you need to consider is that, well, the pipe. Okay, you can have vertical pipes or you can have horizontal pipes. In the case of a vertical pipe, you're going to have a difference in the positions. Okay, I know this thing is so slow. Okay, in the case of a vertical pipe, you're going to have a difference in the vertical positions. So imagine that this pipe is 2 meter long. Okay, so the difference in the position is going to be 2 meters. Okay, and the position, the first vertical position is going to be 0, and the position of the second one is going to be 2. Those are things to consider in Bernoulli's equation, the position of the pipe. Also, in the case of a horizontal pipe, what happens with y? What is the difference in the position in a horizontal pipe? They are exactly located in the same position. Okay, position 1 is equal to position 2. So what happens when you get the difference in the difference in position is gonna give you 0 meters. When this occurs, when you have a horizontal pipe, what is going to happen? The third term of Bernoulli's equation, that is about potential energy is going to be 0. Now, one other thing to consider is imagine that you have in one side of the exercise you have a river, okay, and it has a speed. Whatever speed, okay? And then in here you have a pool. So what happens between the river and the pool? The river has a speed. If it has speed, that means that it has kinetic energy. In the case of a pool, the water is at rest. Water is not moving in a pool, okay? So what's going to happen here? The kinetic energy is going to be 0 because the velocity of the fluid in this pool is 0, okay? So those are situations that you need to consider for Bernoulli's equation. Now, what do we need? It says Bernoulli's equation is this one: pressure 1 plus 0.5 density, velocity 1 squared plus density, gravity, position 1 equals to the same but 2. Okay, because we have in this exercise, we're talking about a horizontal pipe. Okay, we're talking about a horizontal pipe, and we already said that in the case of a horizontal pipe, the potential energy is going to be 0. Okay, so what's going to happen? We're going to focus on that part of the potential energy of the equation, and we're going to get rid of those terms. Why? Because it is a horizontal pipe. So now the equation is being reduced to this: pressure 1 plus 0.5 density, velocity 1 squared equals to pressure 2, it looks like density, plus 0.5 density, velocity 2 squared. Okay, if you analyze your given, you'll notice that you're missing the velocities. Okay, here I just give you the flow rate, I just give you the diameter slash radius. Okay, from the radius you can get the area, but I don't give you the velocities, and you need velocities. Okay, how do I know that I need velocities? Because it says water flows. If water is flowing, it has a velocity. Okay, so I need to find those velocities. To find those velocities, you need to focus on the flow rate. And why the flow rate? Because from the flow rate, Q, we have the definition of flow rate to be area times velocity. So if you want to find the velocity 1, you're going to use the point 1. And if you want to find velocity 2, you're going to need the point 2. So I'm going to isolate velocity 1. Area goes to the other side to divide. So Q1 is going to be equal to, Q1 over area 1 is going to be equal to velocity 1. If you make substitution of your given, it's going to be 4.17 times 10 to the negative third power, negative fourth power, cubic meters per second. Okay, what is my area? The area of the pipe. the area of the pipe is 0.0038. Square meters. This is going to give me velocity 1. How much is this? And you will do the same for the velocity 2. The velocity 2, you're gonna need the area too. 0 point? Okay. Now take a look. The area 2 is given us in centimeters square. Okay? But remember, these are centimeters square. You need to convert to meters. But also, these are not linear units. You need to raise them to the second power. So the area 2 is this one, 0.003. It's 30 divided by 100 to the second power. Okay? It is 0.003. So you calculate with this velocity 2. When the class is over, please come back to the meeting so we can finish the exercise. How much is that? 0.14 rounded. 0.14 meters per second is going to be the velocity in my point 2. So with these velocities, I'm going to use them in the main equation. What do I need to find? I need to find P2. Okay? I need to find P2. This is my unknown. Now I have the velocities. I know the density. All I need to do is replace it by the givens that you already have. The pressure 1 is 6 pascals. So I say 6 pascals plus 0.5, the density that is 1000 kilograms per cubic meter, times the velocity 1 that we got from here, that is 0.11 meters per second. And this velocity, as you can see in the formula, is raised to the second power. This is equal to what I have in the other side, pressure 2 plus 0.5, the density, times velocity, that is 0.14 meters per second square. Okay, 0.14 meters per second, raised to the second power. Okay, how much do you get from this multiplication? Guys, how much do you get from that multiplication?
7.
No. Only from the yellow part. Only from the yellow part. Okay, remember that is 0.11 is raised to the second power. 6.05. Yeah, if you add plus 6, yes, it's gonna give you 12, but just that part of the formula, that part of the procedure gives you 6.05 pascals, right? Only the yellow part, I mean. Do you get the same answer as me? Okay. Now, what do you get in the blue part? Don't forget that it's raised to the second power.
9.8.
9.8. Okay? So I need to isolate P2. The 9.8, as you can see, is making an addition, so in the other side is going to be subtracting. So you will have 6 pascals plus 6.05 pascals minus 9.8 pascals is equal to the pressure. But this 9.8 was doing a subtraction, an addition, so it goes to do a subtraction to the other side of the formula. That's the only part of the formula that I moved. How much? This total, how much is that? 2.25. Don't forget that those velocities are raised to the second power. And don't forget the isolations, okay? If 9.8 pascals is adding in one side, to the other side is going to go and make a subtraction. Mami, shh. Okay, so guys, do you get the same answer as me? Just be careful on that. Remember, to find the velocities, that's why they give us the flow rate. Flow rate has nothing to do with Bernoulli's equation, as you can see. It's not part of the equation. But it helps us to find the velocities that we actually need to find the requested pressure too. Do you have a doubt with this exercise? If not, we can go in peace.